Section 3.7 is on page 299 in the book, talks about derivatives of inverse trig functions. So we have here two types of functions we're going to be really focusing on. One is the general inverse of a function, and the second is the inverse trig function specifically. So if you recall, in an inverse of a function, we switch x with y. That's really how things work. And let me just move this down really quick. So the inverse of a one-to-one function, if you recall, is a relation in which the x and the y switch places. So this is how we're going to use this for the most part. If this is f, this is the point a, b. In the inverse, you simply swap them. So the domain of the original becomes the range of the inverse, and the range of the inverse becomes the domain of the original, and vice versa. Now, as far as graphs, it's kind of simple to really do this. It says, sketch the inverse of a function. Well, it's fairly simple. Let's do that in purple. Since it's a straight line, find any 2 points. So say that point right there. That is 0, -3. And an exact point, say that's 2, 1. Switch x with y. If you switch x with y, that becomes -3, 0. And switch x with y, that becomes 1, 2. If it's a straight line, connect those with a straight edge, a ruler, and there's your inverse. Now you should know a graph and its inverse is symmetric with respect to the line y equal x. If you draw a line cutting the quadrant exactly in half, the graph of f and its inverse should be symmetric. That means if you take one of them, paint it, and fold it about the line y equal x, it should overlap. 262 is another one of those. Well, let's see again. We find few points. We know that this is getting close to this asymptote. So this is y equals 0 is an asymptote. X equals 0, because you switch x with y, will be an asymptote. This point is 0, 1. So 1, 0. And what do you think this point is? It looks like 1, 0.2. So 0.21, right? And then 2, it looks like almost 0.01, 0.012. So the graph here looks like from the asymptote down. And this point, what do you think this point is? That looks like -1/2, 2. So 2, -1/2. And what do you think this point is? It looks like -1, 4. 1, 2, 3, 4, -1. There's the graph. If you draw the line y equal x, cutting the quadrant exactly in half, you'll notice that those two will overlap. This will overlap with this, and this will overlap with this. So just switch x with y, and that's your graph. Now, this is where we're going to use, oh, and part B, I almost forgot. It says part B, and we want to start getting used to this. Part B, they want us to find the slope of the tangent of the inverse of this graph at 1. Well, at x equal 1, wouldn't that be the slope of this line? If it's a straight line, well, pick any 2 points on it. Rise over run. So in this case, since it's a straight line, that's simple. The derivative of the inverse evaluated at 1, in this case, it's rise over run, 1/2. Graph-wise, it's kind of simple. And if you go to this one, the inverse was the graph that I sketched. I want the derivative, and again, this is the inverse of x. This is the inverse of x. So at 1, you're trying to figure out the slope of the tangent, the slope of this line. Again, this is not going to be exact here because you're approximating. A straight line you could figure out, but let me use a different color. So the slope of the tangent at 1, if I draw a tangent line here. a line that touches the curve at one point. So as you see, this is an approximation, and we're going to say f the inverse of 1 is going to be, well, let's see, at x equal 1 specifically. That is, it looks like, if I'm going to say those 2 points, you're going to rise 2 down and 2 to the right. Again, this is an approximation. But for the rest, we're going to find exact, and here it is. This is the theorem we're going to use all throughout this chapter, or this section, I should say, mainly. It's okay, let's leave it like that. This is what it says. It says, given that a function f is differentiable 1 to 1, that means for every one x, there's exactly one y. That's the restriction for you to have, for inverse to exist. And the inverse of that is f with a negative 1. Again, that's indicating not 1 over, that's the inverse of x. And this here does not equal 0. If I want to take the derivative of an inverse function evaluated at a, notice what that theorem says. It says it's 1 over the derivative of f. This is nothing more than a number. And let me elaborate. If this is f, if you pick a, y will be f of a, right? This is the inverse. If this is a, if this is b, this is f inverse of b. But the way those are related, don't you swap the x with the y? So whenever you say in the original, I want x equal a, you're saying in the inverse y equal a, and vice versa. Now, I want to go backwards. This says I want the inverse of a. Yeah? If I go this way, and I know it's hard to think backwards, what does this x become? Doesn't that become the y? So we're not really looking in this direction. We're really looking, now that I explained this, we're looking in this direction. We're looking at this value that I marked in yellow is saying find the y value in the inverse when x equal a. If I don't want to go in this direction, I want to go in this direction. Doesn't that mean whatever this x, that must be that y? So I need two things. I need the derivative of f, and I need that y value. But that y value is the original x value when I switch x with y. I know this is confusing, but let me show you. So here it says find the derivative of the inverse at 2. According to the theorem up there, that's 1 over the derivative of f. So let me work from the inside out. Let me figure out what this equals. According to what I put up there, we're trying to find the inverse. There. I'm trying to figure out the y value in the inverse when x equal 2. If I go to the original, don't you switch x with y? Don't they swap? There it is. If y equal 2, there's y. If y equals 2, what does x equal? Well, if I solve that equation, what do I get? So I'll get x to be 0 or negative 3. But they tell me the restriction on this problem is that x is greater than negative 3 halves. Negative 3 halves is negative 1.5. X is greater than that. It can't be that. Since this is 1 to 1, there could only be one answer. I got this point to be 0, 2. If x equals 0, look at this problem. If I put 0 in there, isn't y 2? Now, doesn't that mean when I go to the inverse, when x equals 2, that's 0? So guess what? That's the trick. I just figured out what this equals. So this is saying now, if I really read it, this is saying 1 over f prime at 0. What's f prime? There's f of x. F prime is 2x plus 3. If I evaluate that at x equals 0, what do I get? Isn't that a 3? And what did I just figure out? I figured out the derivative of the inverse function without finding the inverse. Massive deal. Again, I found the derivative of the inverse without finding the inverse. That's what the theorem does. So this is something like inverse is not opposite. Inverse is undoing what you did. So this is figuring out the rate of change and backtracking your steps. So if moving forward is, I suppose, taking a submarine underwater, then the inverse will be bringing it back. Here's another problem. What I want to find the derivative of the inverse evaluated at 2. That is 1 over the derivative of f evaluated at 2. Well, let's see. Let's figure out what this is. That's a number. Let's figure out what this is. That's a function. That's a derivative. Well, let's go on the side and do this, and it doesn't get old. If this is f, this is the inverse. That's the most confusing part of this problem. If I look at the green part, it's asking me to find the y value of the inverse when x equals 2. If I translate that into that original, don't you switch x with y? Doesn't that mean that that's 2? And whatever this number is going to translate into the y. Well, let's see. Y equal 2. So if I take this y and I put a 2 there, 2 equal x plus radical x. 0 equal x plus radical x minus 2. This factors, by the way. So I got radical x plus 2 equals 0, or radical x minus 1 equals 0. Radical x equal negative 2, that's not possible. Radical x equal 1, square both sides, x is 1. If x equal 1, that means in the inverse, this value is a 1. Okay, I got that. What else do I need to figure this problem out? I need a derivative of the original function. Well, that's one thing I need. I need a derivative. What's the derivative of the original function? There's the derivative. Well, there's the function. 1 plus 1 over twice radical x. I'm going to evaluate that at the 1. That is 1 plus 1 half, which is 3 halves. So the derivative of the inverse now, evaluated at 2, is 1 divided by 3 halves, and we know that 1 over a fraction is the reciprocal, and that's my answer. Again, I just find the derivative of the inverse function without finding the inverse. Finding the inverse is a lot of work, and sometimes it's not even possible. And how about this problem? The same deal. Again, this doesn't get old. This is f, this is the inverse. When I want to find the derivative of the inverse evaluated at 0, that's 1 divided by the derivative of the function. What's the derivative of the function? It's 1 plus cosine of x. There, that part is done. Evaluated at, so here, by you saying I want to find the y value in the inverse when x equals 0, in the original, doesn't that mean you're setting y equal to 0? So where would 0, let's go this way. where would 0 equal, put a 0 right there for y, x plus sine of x. Well, if they gave you that without a graphing calculator and you're not allowed a graphing calculator, it has to be one of the basic angles. Well, that's at x equals 0. If I put 0 in there, isn't that 0 plus 0? There we go. Now what? Well, now I figured out that if the x in the original is 0, that's that value. So now I'm looking for 1 over f prime at 0. There's f prime. If you put x equals 0, what do you get? Isn't that 1 plus 1, which is 2? And there's my answer. All right. Now, the rest is really straightforward. Now, in my class, and again, that's me, I provide this table on your test. You really don't need to memorize. I need you to memorize just the sine. And do you see that cosine is the same thing with a minus? The rest, I'm sorry, take that back. Forgive me. I provide those four for you. You don't need to memorize those. But you need to memorize this. This you need to know. And the reason I have you know it, because it comes up all over. We see this a lot more than we like. And the cotangent is simply that with a negative. So I need you to remember this and the cotangent. That I don't provide. But those I provide on your test. The inverse, derivative of inverse sine, inverse cosine, inverse secant, inverse cosecant. Now, if I'm providing this, you just have to remember the inverse derivative of inverse tangent of x is 1 divided by 1 plus x squared. Now, make sure you understand, inverse sine of x does not equal 1 over sine of x. That equals arc sine of x. So, if I want to take a derivative of this, chain rule, now that you know about the chain rule, it's never going to go away. Derivative of inverse cosine, it's right there. It's negative 1 divided by the square root of 1 minus whatever this is squared. Now by the chain rule, since that's not an x, times the derivative of the angle, which is 1 over twice square root of x. And you could clean it up a bit. You could say that equals negative 1 over twice. And you could combine those radicals if you wish. You don't have to. You could say that's the square root of x times 1 is x. And this is x times x, that's x squared. Or you could just leave it as is. That's not an issue. And if I would like to take a derivative of 282. Well, derivative, the outsidemost function is a radical. Derivative of a square root specifically is 1 over twice the square root. We agreed you were going to memorize that. Times derivative of cosecant of x. Cosecant of x is right there. The derivative, just copy that down. Times negative 1 divided by x, the square root of x squared minus 1. And there it is. That's all we have to do. Now that you know about the chain rule, it's never going to leave you alone. When do you apply the chain rule? On every single derivative you will ever take. How about this problem? If I want to take a derivative of inverse secant dy dx, where's inverse secant? Inverse secant is right there. It is 1 divided by, okay, it's not x, it's negative x. So negative x, the square root of negative x squared, that's still x squared, right? Since that's not an x, by the chain rule, derivative of negative x is negative 1. And the negatives cancel out. And there it is. And if I want to take a derivative of x times cosecant, well, let's see. In this case, it's going to be the product rule. Derivative of the first times the second plus the first. What's the derivative of cosecant? Derivative cosecant is negative 1 over x square root of x squared minus 1. Now, you notice that those cancel out. And there it is. Anywhere I use the chain rule, you could let u equal the inside and y equals square root of u. You could do that all the time. And here you could let u equal negative x and y equal inverse secant of u. And proceed like we did. We have one application problem. It's kind of fun. Kind of. Depends on who you ask. Well, a building that's 225 feet tall casts a shadow of various length of x depending where the sun is as the day goes by, correct? And the angle of elevation, just so you would know, angle of elevation is when I'm looking straight and I look up. That's called angle of elevation. Angle of depression is when I'm looking straight and I have to look down. So if I'm standing at the top of the building, I have to look from straight, I have to look down. That would be the angle of depression. You need to know those. And if I'm standing on the floor, I'm looking at the top of the building, that's the angle of elevation. So here they gave you the diagram. They didn't do that a lot. Just want to point that out. It's formed by the line from the top and the bottom of the building to the tip of the shadow. Okay, there it is. They marked it as seen in the figure. Find the rate of change of the angle d theta dx when x is 272. So again, at different values of x, the angle is differing. If you wait, if the sun is here, when it's daytime and the sun moves, the angle changes, which means this is varying. Well, let's see. I need a trig function that combines an angle, the opposite, and the adjacent. Tangent of theta is the opposite over the adjacent. And wouldn't you say theta will equal the inverse tangent of 225 divided by x? Now what? If I take a derivative, d theta dx, what's the derivative of inverse tangent? 1 divided by 1 plus whatever that angle is, squared, times by the chain rule. What's the derivative if I take 225 divided by x? Isn't that 225x to the negative 1? Bring the power down, subtract 1 from the power. So there it is. D theta dx will be 1 divided by 1 plus 225 over, what's x? 272. Right? And what would that be? Parentheses? No. Yeah, the top. Negative 225 divided by 272 squared over 1 plus 225 divided by 272 squared. That'll be the answer in exact. And if I want the approximation of that, that's negative 1.81 times 10 to the negative 3. And that would be radians because theta is in radians, and x we said was in feet. And there it is. And that's the suggested homework that I'd like you to do.